Welcome to the presentation of our paper for the 2020's IEEE workshop on detection and classification of acoustic scenes and events. Our paper is titled Anomalous Sound Detection as a Simple Binary Classification Problem with Careful Selection of Proxy Outlier Examples. My name is Primus and I'd like to thank my co-authors Verena, Patrick Braha and Gerhard. Our work is concerned with anomalous sound detection for machine condition monitoring, which, from an abstract point of view, can be seen as a general anomaly detection problem. To put it into a nutshell, anomalous sound detection is the following problem. We're given an audio signal, which is fed into an anomaly detection system, which then predicts if the sound is normal or abnormal. Optionally, the system could also output an anomaly score, which reflects the system's degree of belief if the given sample is normal or not. Candola gives a good definition. In his survey paper, he defines an anomaly as a pattern which differs from what is regarded as normal and which, in contrast to noise, is of interest for various downstream tasks. In machine condition monitoring, normal data are all sounds emitted from the machine in a normal operation mode. Anomalies are those sounds which the machine emits when the machine is broken. And noise are sounds from a non-broken machine which contain unusual patterns such as noise from a factory environment. Our goal then is to train a system which can distinguish between sounds from an operational and a broken machine. Note that the terms anomaly and outlier are often used as synonyms in the literature, and we do the same in this presentation. Now that we have defined the task, let's talk about the tricky part, which is the training of such an anomaly detection system. If the types of anomalies are restricted to a few and labeled normal and anomalous training data is available, the task of learning an anomaly detector boils down to supervised training. This scenario is what Agarwal refers to as supervised anomaly detection. The main challenge in supervised anomaly detection is the unbalancedness of the dataset, because outliers are relatively rare compared to normal data. However, in real-world scenarios such as machine condition monitoring, anomalies are highly diverse and therefore we cannot restrict them to just a few types. This makes deliberately collecting a representative set of anomalies unrealistic. This is commonly solved by disregarding outliers and creating a model of the normal behavior by using only normal machine sounds. Agarwal calls this setting the unsupervised anomaly detection setting. Popular methods in this area are based on unsupervised machine learning, for example based on the reconstruction era of variational autoencoders or based on density estimation. As an alternative to these approaches, we propose to substitute anomalies with non-target machine sounds. Those are arbitrary sounds from the audio domain which are neither normal nor abnormal. Doing so allows us to train the anomaly detector with supervised methods. We call this carefully substituted sounds proxy outliers. In practice, this boils down to first selecting a set of proxy outliers, then training a classifier to distinguish between normal machine sounds and proxy outliers, and finally using this classifier at prediction time to distinguish between normal and anomalous machine sounds. By merely training a ResNet to distinguish between normal machine sound and carefully selected proxy outliers, we achieved the third team rank in task 2 of the 2020's DCASE challenge. This is especially remarkable as we did not apply data augmentation, transfer learning, model assembling, or sophisticated post-processing. Why does this work? Well, there are several possible explanations for these results. Roof, for example, does similar experiments in the image domain and finds that a classifier trained to distinguish between normal sounds and 64 randomly selected images is able to outperform state-of-the-art methods on the ImageNet anomaly detection benchmark. In their experiments, they attribute this informativeness of proxy outliers to their variety and to low-level features in the images. We hypothesize that proxy outliers, which are not trivially distinguishable from the target sounds, lead to a discriminative feature representation in neural networks, which are then useful for the anomaly detection task. We conducted a series of anomaly detection experiments with machine sounds. The main goal of our experiments was to identify which task-unrelated data can be used as proxy outliers. For the normal machine sounds and testing data, we used the DCASE 2020 Task 2 development set, which is actually a combination of the MIMII and the Toy Atmos datasets. The MIMII dataset contains recordings of 4 different machine types, and for each machine type, normal and anomalous data for 4 individual machines is given. This means the dataset contains recordings of 4 different fans, 4 different pumps, and so on. Let's listen to one of the valves. I assume that the clicking sound is produced by the valve. We can also hear a static background noise. For comparison, here's a sound snippet from another valve. This time the type of background noise is different, but the clicking sounds are very similar. And for completeness, let's also do a short direct comparison between normal and anomalous sounds produced by the same valve. Again, here's the normal sound. And the anomalous sound. As you could hear, there's almost no difference between the normal example and the anomaly, except for the background noise. The only difference I got is that the clicking in the anomalous example is slightly dampened. The Toy Atmos set contains recordings of toy cars and toy conveyors. In total, the set contains recordings of 4 individual toy cars and 3 individual toy conveyors. In our experiments, we trained a separate anomaly detector for each of the 23 individual machines. We use a part of each machine's normal data in conjunction with proxy outliers to train the anomaly detectors, which are actually just classifiers. The rest of the normal data and the anomalies are used for testing only. To train the classifiers, we also needed to create candidates for the proxy outlier sets. For our experiments, we built 6 candidate sets for each of the 23 machines. The first 3 proxy outlier sets are created such that the recording conditions are equal to the recording conditions of the target machine's normal data. By equal recording conditions, we mean similar setup and equal microphone hardware. Since MIMII and Toy Atmos were recorded under different conditions, we make sure to not use MIMII data if the target machine is from Toy Atmos and the other way around. I'd like to stress that no anomalous machine sounds were used as part of the proxy outlier set. The first proxy outlier candidate set is composed of normal recordings of machines of the same type as the target machine. For example, if the target machine is fan 1, then the proxy outlier set contains the normal recordings of all other fans. In this scenario, the proxy outliers are semantically very close to the target data. In the second scenario, the proxy outlier set is composed of normal recordings of machines of different type as the target machine. For example, if the target machine is fan 1, then the proxy outlier set contains normal sets of pumps, sliders, and valves. Recordings of other fans are not part of the proxy outlier set. In this scenario, the proxy outlier set is semantically further away from the target machine's normal data. The third proxy outlier set with matching recording conditions is a combination of the previous 2 sets. This means the proxy outlier set contains normal machine sounds of machines of all types. For example, if the target machine is fan 1, the proxy outlier set contains all the other fans and also recordings of all pumps, sliders, and valves. Furthermore, we experimented with 3 proxy outlier candidates with mismatching recording conditions. Firstly, we used the Toy Atmos dataset as proxy outliers for all target machines in MIMII and the other way around. The recording conditions in these proxy outlier sets are constant, but not equal to the recording conditions of the target machine set. The variety of sounds in this proxy outlier set is rather low. Secondly, we use the Tau Urban Acoustic Scenes 2020 mobile dataset as proxy outlier set. The dataset contains recordings from 3 real and 6 simulated devices. The variety of sounds in this dataset is higher than in Toy Atmos and in MI. Thirdly, we also experimented with the balanced version of audio set. This dataset was collected from YouTube videos. It therefore presumably contains recordings from a large number of devices. It contains audio snippets from a lot of different domains, such as music, wildlife, or traffic. The audio preprocessing is rather standard. We resample the audio signal to 16 kHz and normalize each sample to have unit variance. We then compute a short time Fourier transform using windows of size 1024 samples and a hop size of 512 samples. We weight the resulting power spectrogram with a Mel-scaled filter bank of 128 filters and applied a logarithm to dampen large outliers. We chose the model architecture introduced by Coutinho et al., a receptive, regularized, fully convolutional residual network, which has been successfully adopted for various audio-related classification tasks. Training of the model is performed on random snippets of 256 frames length. We minimize the binary cross entropy for 100 epochs using Adam update rule with a batch size of 64. Batches are stratified to contain 32 normal samples and 32 proxy outliers. During one epoch, the network sees all normal samples. Proxy outliers are drawn randomly. We set the initial learning rate to 10 to the power of minus 4 and decay it every epoch by a factor of 0.99. For each baseline method and each variant of the proxy outlier dataset, we train 3 anomaly detectors on the normal data of each machine. To compare our methods, we computed the area under the receiving operating characteristics curve on the test sets. For a more comprehensive visualization, we averaged the results over the machine type. The 2 blue bars represent the results of the baselines. Dark blue is a baseline based on reconstruction error of a variational autoencoder, and light blue is a density estimation baseline based on normalizing flows. Orange bars illustrate the results of proxy outlier candidate sets with matching recording conditions, and the green bars the results with mismatching recording conditions. By looking at the dark orange bars, we can see that sounds from machines of the same type seem to be especially useful. One possible explanation for this is that those sounds cannot be trivially distinguished based on high-level statistics. The classifier therefore has to focus on low-level features, which are then more useful for the anomaly detection task. Using sounds of different machine types sometimes leads to a substantial drop in the performance, as we can see from the light orange bars, especially for the machine types slider, toy car, and valve. This could be explained by the fact that the sounds of different machines are too dissimilar to the target sounds. As a consequence, the classifier might be able to distinguish between normal sounds and proxy outliers based on simple statistics and does not learn discriminative features for anomaly detection. For the proxy outlier sets with mismatching recording conditions in green, we see that the performance is positively correlated with the diversity of recording conditions and the diversity of content. However, proxy outlier sets with mismatching recording conditions are almost always inferior to those with matching recording conditions. We also investigated the role of the proxy outlier set size. We started with 4 samples and gradually increased the proxy outlier set size to the maximum of 16,000 samples. On average, our method outperformed the autoencoder baseline with only 128 proxy outliers and the normalizing flow baseline with only 512 proxy outliers, except for toy conveyor. In this study, we showed that carefully selected proxy outliers can be leveraged to frame the task of anomalous sound detection as a simple binary classification problem. In our machine condition monitoring experiments, we find that matching recording conditions, similarity to the target sounds, and content diversity make proxy outliers especially informative. We also show that relatively few proxy outlier samples are needed to outperform unsupervised baselines based on reconstruction error and density estimation. Thank you for your attention, and I'm happy to answer your questions.